Okay, so we're in part 2 of chapter 7. We're going to finish this out. The next type of reaction that we're going to talk about is an oxidation and reduction reaction. Now, oxidation reduction or redox reactions are essentially the same as single replacement, synthesis, or combination or decomposition reactions, and also combustion reactions. But they're focused on looking at the transfer of electrons. And so if you look at this slide, rusting is an example of an oxidation. Iron is oxidized by the oxygen in air, and the electrons are transferred. And so hopefully you remember that electrons being transferred should sound familiar to you, because that is the process in which an ionic compound is formed. So we're looking at this formation of this iron oxide here. An oxidation and reduction reaction happens with combustion reactions, and so when we eat food, those are combustion reactions. And then we have electrical energy in batteries. Those are typically single replacement reactions, where we have electrons being transferred, making electrical energy by those electrons moving. And then iron rusting. Now, if we look at this type of reaction, take a second to identify the type of this reaction. This is a synthesis or combination reaction. And so looking at what's happening to the iron in this case, we can figure out what's happening to the electrons. So looking at the iron, over on the left side, on the reactant side, the iron is neutral. So let's think about what the charge is, because if we're tracking electron movement, it's helpful to track the charge of the compound. And so here the charge of the oxidation of the iron is 0. And so the charge that we're looking at here, it's called an oxidation state, but it's essentially the charge if an element would have a charge. And any element that is neutral, called a free element, that is kind of just existing normally like it exists in nature, has a neutral overall charge. And so the iron on the left side would be neutral. The oxygen on the left side, the reactant side, is also in its elemental form, so the charge would be 0. So we're going from charges of 0, neutral things, to an ionic compound. So this is an ionic compound, and we need to identify the charge of the iron. So you can do that in a few ways: reverse crisscross, you can think about mathematically, but I know that oxygen is always -2 as its charge. And I have 3 oxygens at a -2 charge. I need to combine that with 2 irons, and I don't know the charge of iron, so I put an X there. I know this has to add up to 0. And so then I get 2x minus 6 equals 0. 2x equals positive 6, therefore x is equal to positive 3. So the charge of this iron is 3 plus. I would call this iron 3 oxide. The charge of the oxygen is -2. So then we can look carefully and closely at what is happening to each of these elements. So kind of picking it apart, what is happening to the iron? The iron is turning from 0 into positive 3 or 3 plus. So is the iron gaining or losing negativity? If I'm getting more positive, I'm losing the negativity, so this is a loss of electrons. Versus the oxygen is going from 0 to -2. If you're getting more negative, you must have been gaining electrons. And so I can kind of think about where my electrons are being lost and where they're being gained in this reaction. So in oxidation-reduction reactions, electrons are transferred from one substance to another. So they're going away from the element where they're being lost, and they're going toward the element and where they're being gained. And you can think about this as a process that happens together. And so oxidation and reduction, we call it redox because it does go together. If you lose electrons, someone else must be gaining them. So you can remember oil rig, oxidation is loss, and reduction is gain. Now I personally prefer another nickname, which is Leo goes grr. And I think of Leo as lose electron oxidation, gain electron reduction. And I think of a little baby lion. His name is Leo. And he's very cute. And it is a cute thing, a good thing, a positive thing to see this little baby lion. He's so cute. And so losing electrons is more positive, right? This is a positive thing. But if I hear grr while I'm hanging out with my new friend Leo, then I may have a papa lion around, and that papa lion is not very happy because I'm messing around with his baby. So grr is a negative change. And so if you see something becoming more negative, it is grr reduction, which is bad. Or not bad, but just a loss of gaining of electrons, right? But we can think about negative as being bad or grr, right? So here's an example of oxidation and reduction. The Statue of Liberty, she used to be copper colored. So like the color of a brand new shiny penny. That's what the Statue of Liberty was originally created to be. There's the green patina, as we call that. The word patina is this kind of, y'all, it's essentially rust. It's just a fancy word for rust that happens when you have something really old that oxidizes over time. We don't call it rust, right? But it's essentially the same kind of idea. The oxygen from the air is mixing in with the copper and making copper to oxide. And so because of this, if we look at this type of reaction, right, 0, 0, positive 2, negative 2 for your charges, you see there's a change in charge. If there's a change in charge, then electrons are being transferred, and then you have an oxidation and reduction reaction. And so we can look at these two, what we call half reactions. So these are called half reactions. And you can see we kind of split the oxidation and reduction apart. The copper is going from 0 to positive. So it must be losing electrons. So how many electrons is it losing? Well, the copper is going to copper 2+. So originally it lost 2 electrons. But I have to make sure things are all evened out. I have to make sure that they're balanced. If I'm losing electrons, I have to be gaining the same number of electrons. But because I have an O2 on the left side, I have to make 2 oxygen ions on the right side. And so that's a total of -4 charge. So there must be 4 electrons that get gained for that. Now you don't need to worry about balancing out half reactions, but you should think about where the electrons are being produced in the oxidation step, and then electrons are being used in the reduction step. So we don't actually include the electrons in your overall reaction because they're being produced and used at the same time. So here's another example. We will see some things like this in our lab. You've got some solutions. I've got copper and sulfate solution, so a copper 2 sulfate. I put the zinc in to the copper 2 sulfate solution. The copper 2 ion is going to replace the zinc. So the copper 2 ion turns into copper metal, and the zinc leaves as an ion. And so the copper is in solution, and the zinc is going to replace the copper in solution. So think about the sulfate hanging out here. The sulfate is going to be with the more active metal. So if you look at your activity series in your periodic table, the metal that's on the top is going to get with the sulfate. So you have an option of copper or zinc. If you look at that periodic table, zinc is higher. So the sulfate would rather be with the zinc. So the sulfate is going to take the zinc ion, right? And it's going to kind of go to be with the sulfate. The copper is the one that's going to get replaced in. So the copper is going to get left on its own. And we'll talk more about this in class, but the activity series and single replacement reactions. So go ahead and take a second and pause and tell me if this is oxidation or reduction for each of these individual reactions. So coming back from your practice, if I look here, 10, 0 is going to 10, 4. Is this a more positive or negative change? This is a more positive change, so this is Leo. Leo's for oxidation. You can also see the electrons are being produced. Products are the same as lost, right? So if I lose heat or if I lose electrons, then they're going to be as a product, right, going out. Looking at the next example, iron goes from 3 to 2. That got more negative, so that's GR reduction. You could also see that your electrons are hanging out in your reactants. And so electrons in the reactants is something that's going in or being gained. So you look in here, chlorine is 0 and it's going to -1. Again, that is reduced because it's getting more negative. So let's look at this next example. I'm going to pause and take a look at it. Okay, so coming back, which is oxidized and which is reduced. So sometimes ultraviolet light is needed to make a reaction go, and so you write it over the arrow saying like, hey, we need this to go. So sometimes you'll have a triangle over the arrow, meaning you need some heat to get this to go to happen, but here we need ultraviolet radiation to make this happen. So I start with my silver as a +1 charge. I start with my chlorine as a -1, and then it goes to silver neutral and chlorine neutral. So we need to figure out what's being oxidized, what's being reduced. So remember, oxidized is Leo, and that is a positive change. Reduced is GR, and that is a negative change. And so my silver is going from +1 to 0. Is that getting more positive or more negative? Well, you pull out a number line if you want to. Don't be afraid to get a number line out if it helps. So going from +1 down to 0, well, this is reduction because it's getting more negative. And so what's getting reduced? The silver ion is getting reduced, not the silver neutral, the silver ion, the reactant. So you must have a reactant that is getting oxidized or reduced. So looking at the chlorine, it's going from -1 to 0, so it's going this way. This way is oxidation, getting more positive, so my Cl-. The reactant chlorine, not the product chlorine, is getting oxidized. There are tons of things in our body that do oxidation and reduction. The biochemical molecule coenzyme FAD, flavin adenine dinucleotide, can be reduced to the coenzyme FADH2 by the transfer of 2 hydrogen atoms. And so 2 hydrogen atoms get transferred with 2 electrons, and you have this loss of hydrogen and this gain of hydrogen. When we're talking about organic chemistry, we're not going to really follow the electrons so much because it's kind of hard to follow those, but we can follow hydrogen and oxygen bonds, and that will help you figure out what's being oxidized and what's being reduced. So, looking at these examples, if you have a loss of hydrogen or a gain of oxygen, that's oxidation. And so looking at these examples here, I have some oxidation reactions. You can see here that this compound, methyl alcohol, CH3OH, goes to H2CO. Well, I had 4 H's to begin with, and I have 2 H's now. So I lost H. You can also see the hydrogen hanging out as a product, meaning it's being lost. If you lose hydrogen, that is oxidation. Another example of how you can figure out oxidation is you can look at your what's happening to your oxygens. And so here I have 1 oxygen and I have 2 oxygens, so I gained oxygen. If oxygen is being gained as a reactant, then I'm oxidation. So here just a quick slide of the different characteristics of redox reactions. Oxidation always involves a loss of electrons, that's your Leo. Or can be seen as the addition of oxygen, so plus oxygen for oxidation, or loss of hydrogen, minus hydrogen. So we're going to think about hydrogen and oxygen as being kind of opposites with water. Losing hydrogen is the same as adding oxygen. Gain of electrons, I want you to think Ger. Loss of oxygen, so if you're being reduced, you're losing oxygen, you're the opposite, and if you're being reduced, you're gaining a hydrogen ion, or hydrogen atom. So the next step for this chapter is talking about molar relationships, and so we're going to build on the first video in the mole relationships and mole conversions, molar masses, and we're going to build on this. And so in a chemical reaction, the mass of the reactants is the same as the mass of the products. And so if I put together 2 irons and 3 sulfurs and I get iron 3 sulfide, well, the combined mass of these 2 reactants would equal the total mass of the product. This is the law of conservation of mass and conservation of matter. The law of conservation of mass says matter cannot be created or destroyed, no change in total mass occurs, and mass of products is equal to the mass of the reactants. We are balancing chemical reactions because of this law, but you can also think about it in terms of in the lab, when you're measuring things, what you get out should be what you put in, unless you've got some reactants, maybe that reactions that don't run quite as well. But essentially the products should be equal to the mass of the reactants if you have a good reaction. So for the conservation of mass, you can see here that if I put in 215.8 silver, 32.1 sulfur, I get 247.9 silver sulfide. And then if you look at the balanced chemical equation, what does this mean? It means that for every 1 sulfur atom, you need 2 silver atoms. And so that kind of gives you a mole-to-mole ratio. Now, mass is not moles, and so be careful. You're not looking at double the mass. We're looking at double the moles of silver required for sulfur. So mass is not necessarily doubled. So here's all the information that you can get from a balanced chemical equation, which is a ton of information. So here's your equation. You can look at the atoms, right? So 2 sulfur atoms, 1 sulfur atom, or you can look at it as a ratio. So if I put 200 silvers in, I get 100 sulfurs have to go in to make 100 silver sulfides. You can also look at Avogadro's number, so we can use Avogadro's number here. And if we can use Avogadro's number, we can use moles. This is going to be the thing we use the most, and so I'm going to kind of highlight this. We're going to be using the balanced chemical reaction as in terms of a mole ratio, and I don't really want you to think about using the masses here from a balanced chemical equation, but you can use them. This is your total mass, this is your molar mass. So be careful because a molar mass is always for 1, and they're doing a total mass here. So I'd like for you just to kind of focus here on the mole relationship from the equation, and then we'll just deal with the mass outside of that. So what do I mean when I'm saying this mole relationship? I mean that the number here is going to have a unit. I would like for that unit to be moles. Now it can be atoms, it can be molecules, but it is easier for us to package things in a mole, right? Versus like a tiny little particle here and there. And so 2 moles of iron plus 3 moles of sulfur give me 1 mole of iron 3 sulfide. This just comes from a balanced chemical equation. And if these things are true, I can also set them equal to each other and make a mole-to-mole factor. So I can say any combination that I want. I can say 2 mole of iron is equal to 3 mole of sulfur. I can say 2 mole of iron is equal to 1 mole of iron 3 sulfide. I can say 1 mole of iron 3 sulfide is equal to 3 mole of sulfur. I can use any combination of these forward and reverse, it doesn't matter which direction you go, and I can build myself another conversion factor inside of a chemical reaction, which is really helpful because if I can find the moles, then I can find the mass using the molar mass, or I can find the amount of particles using Avogadro's number. The world kind of opens up as soon as I get into that central unit of moles. And so we're going to choose, so pause really quick and pick for either of these options. They both say A, this one should say B. So both options A and B, there are 3 options that could be true. And so let's go ahead and look at which ones could be true, which ones are false. Okay, so a multimole fracture for hydrogen and nitrogen, that's how you say in H2 and N2, not dihydrogen, not dinitrogen. That's just the way hydrogen and nitrogen are because they're diatomic. The number that goes in front of hydrogen is a 3, so I'm looking for 3 moles H. Well, this one says 1 mole H, so not that. This one says 3 moles H, this one says 2 moles H, so not that. And so the number here has to stay with the H. And the number here, which is 1, has to stay with the nitrogen. And so you have to make sure that you're keeping all of that true. So the answer here is 2. For part B, between ammonia, this is ammonia. Remember, ammonium has 1 more hydrogen, so it's yummy, and it's positive, and hydrogen. So the number in front of ammonia is 2. So I'm going to look here. Here's the 2, here's a 2, and here's a 2. Okay, so I haven't really narrowed anything down. All of these have the 2 in front of ammonia, which is good. But I want a multimole factor between ammonia and hydrogen. So look at the hydrogen, I need a 3. Well, that's not a 3. Here's a 3, and this is 3 moles of N2, and I'm asking for hydrogen. The number in front of N should be 1, so not this. So 2 is also the answer for this one. So make sure you can kind of go whatever way you want. You can do any sort of converting. No, it doesn't have to be left to right. Reactant to product, it can be reactant to reactant, product to reactant, product to product. It doesn't matter. As long as you've got a balanced chemical equation, you can set an equality using moles as your unit. So let's use it in some math. How many moles of iron 3 oxide can form from 6 moles of oxygen? And so if I set up my equation, how many moles of iron, actually let's do this. I would like for you to practice writing it directly under the substance. So if I want how many moles of this substance, starting with 6 moles of this. And so I'm going to go from here to here. I need a conversion. I need a mole to mole ratio. Where do I find a mole to mole ratio? From the balanced chemical equation. And so I'm going to look at these numbers to give me that mole to mole ratio. Sorry about that. And so 3 to 2 is this ratio. Now I do not need anything about the iron, the 4 iron in front, because I'm not being asked about it, and I'm not given any information about it, so it's there to help me balance, but it doesn't matter as far as my math goes. And so let's write a conversion. So for every 3 mole of oxygen, that equals 2 mole of the iron 3 oxide. And that's all I need. I have one conversion to get me from moles to moles. If I'm not asking you for mass, you don't need molar mass. So let's start with our 6 moles of oxygen. And now notice here I will absolutely write what substance I'm talking about because it matters, because all the units are the same. And so if all of your units here are exactly the same, you have to differentiate them with the substance that you're talking about. And so if I need moles of oxygen to cancel, I have to cancel it with moles of oxygen. So what number goes with moles of oxygen? This 3. Where do I get this from? The balanced chemical equation. 3 moles of oxygen is equal to how many moles of iron 3 oxide? Well, the answer to that question is 2. 2 moles of iron 3 oxide. And so if I want moles of iron 3 oxide and I have moles of oxygen, I can cancel these out and I'm now finished, so I can solve. So I'll have 6 times 2, which is 12, divided by 3, which is 4. I want 2 sig figs. Your mole ratios are counting numbers, so they don't count for sig figs, so 4 moles of iron 3 oxide. Alright, so here's a multiple choice if you want to check it, pause and work, and then come back. So for this one, I want to know how many moles of iron and I'm given 12 moles of oxygen. I don't have any information about the iron 3 oxide, and that's fine because I don't need it. So I can build myself a conversion factor. So 4 moles of iron are equal to 3 moles of oxygen. And that gets me the mole-to-mole conversion that I need, so I'm ready to start. So I have 12 moles of oxygen. Moles of oxygen have to cancel, so they have to go on the bottom. The number that goes with moles of oxygen is 3. I get this number from the balanced chemical reaction. 3 moles of oxygen are equal to some number of moles of iron in the chemical reaction. That number is 4. I get this number from, again, the balanced chemical reaction. And so my oxygens will cancel. My moles of oxygens will cancel, and I'll be left with moles of iron, which is what I want. And so I'll have 12 times 4 divided by 3, which is 16. And I want 3 sig figs because I started with 3 sig figs here. Mole of iron. Yes, you still worry about sig figs. Your mole ratios are counting numbers, so don't worry about that. So the answer is C. Okay, hopefully you're doing all right. We're going to move along. We don't have too much left, but now we're going to add in some molar masses. And so now if you can do mole ratios, now we can talk about molar masses. And so think back to part 1 video, make sure you watch that first, and then we'll be using that information here. Now, your textbook is going to give you this kind of step-by-step. I don't think necessarily that memorizing a step-by-step is going to be helpful to you because you're going to have questions where sometimes you're going to use molar mass and sometimes you're not going to use molar mass. And in future chapters, I may give you a different conversion to use instead of that. And so kind of have your options open when you get into moles. But I do want you to know that if you're changing substances, you must use the mole-to-mole factor, the mole-to-mole ratio. So if you start with substance A and you want substance B, you have to go through the mole-to-mole ratio. So no matter what your ending and what your beginning is, it doesn't really matter, but the middle is typically always going to be a molar ratio, a mole-to-mole factor, which comes from the balanced chemical equation. Right, so here's an example, and I'll take you through this example. Suppose we want to determine the mass grams of ammonia that can be produced from 32 grams of nitrogen in the following equation. And so they give me a balanced chemical reaction. Make sure you can write in balanced chemical reactions because I'm not always going to give the reaction to you. Sometimes I'm going to have you write and balance the chemical reaction as well. So I want to know how many grams of NH3. And so how many grams of this NH3. So I'm going to put the number of grams or the question mark grams right below. If I'm going to be given 32 grams of nitrogen, they don't give me anything about the hydrogen. Totally fine. Don't need it. So I'm going to be going from grams of one thing all the way to grams of something different. Now I do not have a conversion that goes directly from grams of one thing to grams of something else. But I do have a conversion from moles of one thing to moles of something else. That's the way you change substances in chemistry, is through moles. And so I can write a mole ratio. I know that 1 mole of N2 is equal to 2 moles of NH3. And remember, I'm getting these numbers from the balanced chemical equation. So if I need to use a mole ratio, then I need to be in the unit of moles. If I'm given grams, to go from grams to moles, I need the molar masses. And to go from moles back up to grams, I need the molar mass. And so here, I'm going to use the molar mass of N2. So the molar mass of N2 is 1 mole equals 28.02 grams of N2. So 1 mole of N2 is 28.02 grams of N2. And the molar mass of ammonia, so 1 mole of NH3 is equal to 17.04 grams of NH3. And where do I get this from? If you recall from the first part of the video, is you get this from the periodic table, adding up those masses. So now I have all my conversions, and I'm going to start. Starting with the 32 grams of N2, I need grams of N2 to cancel, not just grams, but also N2. And so I need to put grams of N2 on the bottom. The number that goes with that is the molar mass, 28.02. It is equal always to 1 mole of N2. So notice my substance is exactly the same, but my units are different. Well, now I need to get rid of N2 because I'm trying to talk about NH3, ammonia. And so I can say mole of N2 on the bottom, and the number that follows mole of N2 is a 1 because there is a 1 here in the reaction. It is equal to 2 moles of ammonia, and I can cancel my moles of nitrogen. So now I have moles of ammonia. So now I'm talking about what I want to talk about, but I don't have the right unit. I want grams. So I need to cancel moles of ammonia. And the molar mass says that for every 1 mole, there's 17.04 grams of that substance. Now I know that there's a 2 here, but do not bring that 2 down to your molar mass, because molar mass by definition is just for 1, which is why I was telling you in that earlier slide, I didn't really like how they multiplied this together. You should only be using these coefficients for mole ratios, otherwise you'll get very confused and you'll use more conversions than you need and you'll have your answer be incorrect. So canceling my mole of ammonia, I have left over this work, and just like every other conversion factor that we've done before, you're just going to multiply and divide your way across, and you wind up with 39 grams of NH3. I have 2 sig figs because my beginning substance has 2. So why don't you try this one? Pause, try it, and then come back to see the solution. Okay, for the solution for this one, I'm going to set it up. How many grams of oxygen? So question mark, grams under the oxygen. And I need to make 45.8 grams of the iron 3 oxide. Don't need anything about iron. It's not being asked for. So I'm going to go from here to here. Now you don't always have to go from left to right. You can go from, we're going to go making my own point for myself. We are going from right back to the left, which is totally fine. Either direction is great. And then I know I need to use a mole to go that way. So I need to use 3 mole of oxygen is equal to 2 mole of iron 3 oxide. And then to go from grams to moles, I need molar mass. So 1 mole of iron 3 oxide is equal to 157.70 grams of iron 3 oxide. And using the molar mass here, 1 mole of oxygen is equal to 32.00 grams of oxygen. Now I need the molar masses because I'm given mass and I'm being asked for mass. So anytime you're being given mass or asked for mass, you need the molar mass of that substance. So go ahead and start with it. We have 45.8 grams of iron 3 oxide. Grams of iron 3 oxide have to cancel. The number that goes with grams is 159.70. It is equal to 1 mole of iron 3 oxide. Iron 3 oxide, grams cancel, left with moles of iron 3 oxide. So now moles of iron 3 oxide need to cancel. The number that goes there for my balanced chemical reaction is 2. It is equal to 3 moles of oxygen. This should be very familiar to you, this pattern. Moles of oxygen now need to cancel. 1 mole of oxygen is equal to 32.00 grams of oxygen. And I have what I want, so I'm done. So go ahead and solving. 45.8 divided by 159.70 times 3 divided by 2 times 32 is 13.8 grams of oxygen as your final answer. Alright, let's do it again. Pause, work through it, come back, see the answer. Okay, so I want to know the reaction between hydrogen and oxygen produces 13.1 grams of water. So I'm going to write 13.1 grams below water. How many grams of oxygen are needed? So how many grams here? Don't need anything about the hydrogen. And we're going to be moving this way. If I'm going to be changing substances, I have to have a mole ratio. For every 1 oxygen, I make 2 waters. If I'm going to be using moles, I need a molar mass. And I need another molar mass. You're going to start learning molar masses off the top of your head because you do them so many times, hopefully. Okay, so starting here I have 13.1 grams of water. Careful not to use the 2 in front of water here as the molar mass. Molar mass is only just for 1, which is why you can kind of memorize them because it's always the same. So I need grams of water to cancel. The number that goes to the grams of water is the molar mass, 18.02. It's always equal to 1 mole of water. This can cancel out. Grams of water cancels grams of water, left with moles of water. But I don't want water, I want to know about oxygen, so I'm going to keep going. Moles of water need to go on the bottom right to cancel. The number that goes in front of water is 2. And that is equal to 1 mole of oxygen. And this 1 comes from the coefficient in the balanced chemical equation. I can then cancel my moles of water. And I'm left with moles of oxygen. I don't want moles of oxygen, I want grams of oxygen. So moles of oxygen have to go away. 1 mole of oxygen is equal to 32.00 grams of oxygen. My moles of oxygen will cancel, leaving me with grams of oxygen as my final unit. And I can do the math now. So I can set up 13.1 divided by 18.02. Divided by 2 times 32, and we get 3 sig figs 11.6 grams of O2, oxygen. Alright, the last section, energy and chemical reactions. This is a picture of a thermite reaction. You may have seen thermite reactions in movies, TV shows, where someone's trying to break into a lock or a door, and they are like super sciencey or something, and they come up with this like thermite to do, right, to break in. So thermite is just really high temperature. It can actually cut or weld railroad tracks. But it also will melt through locks. So it is something that people do use to break into things, but it's not as used as much as I think as I've seen it on like TV crime shows and like movies of cool things. But it is a thing. So there's thermite. So in order for a reaction to occur, we have to think about what's got to happen. So first, you have to collide. They have to collide in correct orientation, and they have to collide with enough energy. And so what I want you to focus here on this is the energy part. The energy of activation is how much energy you have to put in to get a reaction to go. When I strike a match, I'm providing the activation energy for that match to burn. Is the match burning something that gives off energy? Yes, but I have to get it started first, right? So that's kind of what that means. You have to have an energy of activation. We got to get it. We got to give it a little boost. We got to start it. And so you can have 2 different types of reactions, exothermic or endothermic. So the first reaction here, exothermic. Exothermic, heat is released. So I want you to think that heat is exiting. We notice that the heat is exiting as a product. So I'll actually write the heat as a product, giving you actual number of energy. So kilocalories is an amount of energy, amount of heat. Remember, heat is equal to Q. So if you're looking at this graph, what's happening is I have some energy of my reactants, and my energy of the products is lower, so heat is released. But you see this hump here? That's my activation energy. So this is kind of like burning a match. You have energy of your reactants. We have energy of products. Overall, it's going to give off a lot of heat. But I have to get it started to have it move all the way down. An endothermic reaction is just the opposite. The heat has to go in. So the heat enters or absorbs. So we see it going in as a reactant. So we see here, overall, I have to put energy in to get this to happen. So my activation energy is very high, but the amount of energy I get out is not very much. So it's kind of like a bad investment. I put a lot in, don't really get a lot out. So this is an endothermic reaction, so heat is going in. We see the heat going in as a reactant in the actual equation for this. So tell me if this is endothermic or exothermic. So pause and try. Alright, so in order to tell if something is endothermic or exothermic, we have to first decide where the heat is. So here in A, the heat is on the product side. If the heat is in the product side, it is exiting as a product. So this is exothermic. For the next example, the heat is on the reactant side, so it's entering, so it's endothermic. Now I can give you a number, or I can just say heat. Check out this one. Heat is on the product side, so it is exiting, so this is exothermic. You don't have to worry about any math for this. You do have math for heat. You can do that. But I'm not going to have you do that for these types of reactions. And so how can we make a reaction go faster? You can, a lot of times, heat it up. And so we can make reactions go faster by heating it up, by giving it more energy. Giving it more energy helps it up that hill of that activation energy. You can also increase the concentration of reactants, so you put in more reactants and you can speed it up as well. Or you can add a catalyst. So what a catalyst does is a catalyst lowers the activation energy, so it makes it go faster. So if we were riding bikes and we were trying to get up these hills, if you went up this hill, the purple hill, you would get to the products a lot faster than I would if I'm going up the green hill. And so a catalyst lowers the activation energy, so it makes it easier for the reaction to occur. So here are the things you can do to increase the reaction rate. Y'all know this. Increasing temperature, make it go faster. If you make it go faster, you give it more energy. So you make the energy like up here, I can get over this activation energy a lot faster. You can increase the reactant concentration, so you just have more collisions in general. And adding a catalyst lowers the energy of the activation, so it makes that hill a lot smaller. So tell me whether or not something's going to increase, decrease, or have no effect on the rate of the reaction. So pause and give me some of this. Alright, part A, increasing the temperature. Increasing the temperature gives it more energy. Giving it more energy helps it go up the hill, so that increases. Removing reactants. If you have less reactants, you're not going to go as fast because they're not colliding as much. They have to be running into each other to react. So that would actually decrease. Adding a catalyst increases your reaction rate. Placing the reaction of flask in ice would be cooling it down. Is cooling it going to make it faster or slower? Well, cooling it lowers the energy, so that's going to make it slower. So we're going to decrease the rate. Increasing the concentration of one of the reactants. Increasing the concentration of one of the reactants can increase the number of collisions. But it's best to increase both. But technically you can't increase both. So if your homework is giving you some issues with that, let me know. And so here, we're going to do it one more time, so give us a pause and look at this individual case. Okay, so look at this reaction in raising the temperature. So raising the temperature of this reaction is going to increase it because it gives it more energy to go. Adding oxygen. Oxygen is a reactant, and so it will increase the rate. Adding a catalyst will also increase, and lowering the temperature would slow it down, would decrease it. And then you have a last little concept map to kind of help you stay control of all of the information given to you in this chapter.